Hi everyone, I am Nagendra Bosar. Here today I am explaining you d-Orbital splitting pattern in trigonal complexes. So the trigonal complex is a three coordinated complex, has metal ion at the center of trigonal and three corners of trigonal face was occupied by the three ligand sites. Right. This is what the trigonal complex. And here if when we incorporate the coordination axis xyz, the z axis is passing above of the trigonal face and below of the trigonal face, right? It looks as such the pen, right? This is the trigonal face if we are imagine, and this will be the pen will represent the z axis which is above the trigonal face, isn't it? Right. And it will be below the trigonal face, right? So here the representation may be hard, so we will give you the point, and this direction will indicate the axis which is above and below, right? This was the z axis. And we know that the x axis is left to right. Left to right, the x axis will be there, and front to back, front to back there will be y axis, isn't it? This is the manner we are considering every time the axis xyz axis, right? Left to right x axis, front to back y axis, above and below the z axis, right? Same similarly here also we are considered all three coordination axis, right? So the trigonal complex is three coordinated complex. The metal placed at the center and the three corners will occupies by three ligands, right? The coordination axis when placed on trigonal face, trigonal complex, the z axis will pass through only central metal ion and perpendicular to molecular phase, right? The x-axis will also passes through only metal ion from left to right, and y-axis will passes through metal ion and one ligand, metal ion and one ligand from front to back. So the coordination axes are like this. The z-axis is passing through only metal atom above to below, and x-axis left to right also passes through only metal atom. The y-axis will passes through metal and ligand, right? It will passes through metal and ligand and front to back, right? So this is how the all three coordination axes we have. Now with respect to coordination axis and ligand orientation, we have to describe the how the d orbitals are getting interacted with ligand sites, and which are the orbital getting interacted with ligand sites will get destabilizes and enhances its energy to higher energy level, excites to the higher energy level, and the orbitals which are away from the ligand sites will be stabilizes and reaches lowest energy level. This is how the splitting pattern every time it takes place. So look, let we go for the splitting, how it could be happens, right? We have the 5 d orbitals, and when it is interact with ligand site, slightly it get excited. When the 3 ligand sites get approaches to the metal atom, will forms the complexes where the metal d orbitals are slightly get excites. This represents the free metal ion d orbitals, and this slightly excited d orbitals express the complex d orbital at initial stage, and after this the splitting will takes place, right? After this the splitting will be takes place, right? This would be a zero energy state, right? 0 dq. Now here when we go with the first orbital, or here generally I am going with an dxy orbital, thereafter dyz, dzx, and dx square minus y square, finally dz z square, right? This is how I am going every time. So here also same I am maintaining, right? I am approaching starting with dxy orbital. We know that the dxy orbital has the lobes in between the coordination axis, in between the xy coordination axis, right? So ligand sides, if we consider, the ligand sides are one, the ligand is along the y-axis, the other two looking into an in middle of the xy coordination axis. But actually these two ligands are not at the middle of the coordination axis, right? Isn't it? Why? Because the angle from here, this point to here, right, this will be 180, isn't it? This half circle indicates the 180, right? And when we go with the orbitals lobes, dxy orbital lobes, the dxy orbital is exactly in between the xy coordination axis, right? Xy coordination axis, nothing but the 90 degrees will be bisected by 45 degrees. On the 45 degrees angle, the dxy lobe will be there, right? Dxy lobe will be there here, right? If this is the 90 degrees, right, the 45 will be come here, right, like this, right, like this, right, like here, like here, right? But when we go with the angle between two ligand sites in the trigonal complex, two ligand sites angle, right, bonding angle, this will be 120. We know that this is 120, this is 120, and this is also 120. Angle between two metal to ligand bond is 120. And if we bisect it into two parts, right, 120, if we bisect into two parts, this will be 60 and this will be 60, isn't it? Right. So from the center of this from the center metal to z axis to ligand bonding, it will be 160 degrees, right? Whereas the angle of dxy lobe, which is middle of the xy coordination axis, that will be 45 only. So the 45 angled xy lobe will come here, the 60 angle will be slightly near to this particular x-axis, and this metal to ligand also slightly near towards the this particular x-axis, isn't it? Right. Let me show on one module, right? I consider this, right, trigonal face, right? Here the stick here, it is indicating the z axis, and the middle will be metal, and three corners will be occupied by the three ligand sides. When it come to axis, this is what the top and down, right? Top and down, right, z axis, left to right x axis, front to back y axis, right? This is what the angle, right? This is what the coordination axis. Whereas if we consider the bond, metal to ligand bond, right, they are slightly towards the x axis, right? You look here, here the axis to ligand distance will be very low, right, very low, because the angle, bond angle between this bond to this bond 120, right? Left here and here, after the bonding, whatever the angle it is there between bond to x axis will be what, right? Totally axis to axis, x axis to x axis, 180 degrees, right? From that, if we subtract the 120 degrees of angle of two bonds, right, it left 60 degrees, nothing but here 30 degrees, here 30 degrees, right? So the gap between x-axis to ligand, here x-axis to ligand will be 30 degrees, here x-axis to ligand will be 30 degrees only, right? That is what, right? So where after this, right, keep it this aside. Now come to dxy orbital lobe. Dxy orbital lobe, the dxy orbital is, right, exactly middle of two coordination axis x and y, right? So it will be 45 degree angle, right? It will come exactly here, right? Here the ligand, the lobe will be here, there will be slightly distance will covers from the orbital lobe to ligand, right? And lobe to axis, either it is x or y, it will be 45 degrees, right? Distance will be 45 degrees, right? Here 45 degrees, here 45 degrees. If here if we imagine the lobe here to here, right, if we are imagining the dxy lobe here, right, the lobe to y axis will be 45 degrees, the lobe to x axis will be 45 degrees, whereas the ligand to x axis is what degree it is, 30 degrees, right. So it cannot be, the lobe will not be directly approaching to the ligand side. I want to say that the lobes are not directly towards the ligand sides. Here looking the ligands, maybe if we draw the lobes here in between the coordination axis, it may here looks into, it may looks into the lobe will be along the towards the ligand sides, right, towards these two ligand sides, but actually it is not that, it is not correct that, right. The lobe is slightly towards the ligand side but not direct towards the ligand side, right. There is nearby sidewise interactions will be takes place between lobe of xy to these two ligand sides, right. The lobe will be come here and here, right, here will be the lobe and here will be the another lobe, and here the third one, here the fourth one, right. These lobes may not be interact with the ligand sides because of longer angular distance from here to here, right, the 45 degrees angle, 45 degrees of angle. These two lobes may not be interact with the ligand side of which is along the x along the y axis, but the lobes of here, right, here and here, they may be slightly towards the ligand sides, not exactly towards the, not directly towards the ligand sides, but they are slightly towards the ligand sides, right. So far sidewise partial interactions will be takes place between with respect of these two ligands with the two lobes of xy, right. Have you got, right, this is what happens with the xy orbital, right. The xy orbital lobe is here and here, and it has the angle between 15 degrees of angle between lobe to ligand sides, right, these two ligand sides. So having sidewise will can expected the sidewise interactions here. The sidewise interactions will destabilizes the dxy orbital, and thus destabilized dxy orbital get excited its energy level and reaches to this particular higher energy level, right. So next by we will go with dyz orbital, right. So the dyz orbital, right, yz nothing but this is the y, this is the z axis, right. In between of z and y there will be lobes will be exist, so it nothing but here will be one, here will be second, the donal will be other two, right. So the ligand sides here again, the ligand sides are on plane, right, on my palm, right. But the lobes are how they are, they are two are above and two are will be below, right. Two will be above and two will be below. So far here the lobes and ligand interactions will not be possible here, right. The lobe will be here and downal sides are two, so they cannot interact with the all three ligand sides, they are away, totally away from the ligand sides, right, because of the lobes are above or below of the molecular plane, and they are very much larger distance, covers larger distance from ligand to lobes. So far there could not be any possibility of any interaction with dyz orbital lobe. Similarly, if we go with dzx, thus dzx also has the lobes above the molecular plane and has very larger distance from the uh, ligand size to orbital lobes, so it could also be stabilizes and reaches lowest energy level. Let we see here on picture, right, on module, this is x-axis, this is z-axis, so the lobe will be here, right, above here, right, and here another lobe, second lobe, and similarly downward side there are two lobes, more two lobes, right. These two lobes also, right, these two lobes and above below two lobes also has larger distance from the ligand sides, right, has larger distance from ligand sides. So far they could not interact with the ligand sites, so stabilizes and lowers its energy till the dyz orbital. So far, the dyz and dzx will exist together as a doubly degenerate state in the lowest energy level. Right. So coming to next orbital, right, dyzx. Sorry. Next dx square minus y square. Right. The dx square minus y square has the lobes along the coordination axis. Along the x-axis, two lobes. Along the y-axis, there is another two lobes. Right. This is what x-axis left to right, and this is what y-axis front and back. So here the lobes are left to right on x-axis, front, back, and y-axis. Right. So here on x-axis there is no ligand. So far the lobes along the x-axis may not have any interaction with ligand sites, but the z-axis, along the z-axis lobes it has, and also has one of the ligand site here. Right. This ligand is along the z-axis. Sorry, along the y-axis. Sorry, along the y-axis. Right. Along the y-axis there is an ligand. On the y-axis also there are two lobes. Right. Thus lobe can interact with ligand site of this, so has direct interaction with the one of the ligand of trigonal phase, trigonal complex, will make repulsive interactions with the dx square minus y square orbital, will destabilizes the dx square minus y square orbital in some extent, and thus destabilized dx square minus y square orbital get enhances its energy, get excited in its energy, and reaches to same of dxy orbital lobe. So dx square minus y square also gets destabilizes and reaches to dxy orbital lobe. Here dxy get interacted sidewise with two ligand sites. The dx square minus y square interacting with only one ligand, but the ligand is in direct interaction. So far the two sidewise and direct one ligand interaction will become near equal energies. So far the dxy and dx square minus y square together existing in an higher energy level as it doubly degenerate state. Right. Now coming to the last orbital but not the least, dz square orbital. The dz square orbital also stabilizes, reaches lower energy state, since its slopes also never be have any interaction with ligand z. Right. The dz square have lobes along the z-axis, right, like this, above and below of the molecular plane, has smaller spherical in the middle. Right. The above and below lobes will not have any ligand interaction. Right. On along the z-axis there is no ligand sites. Nearby z-axis also there is no ligand site to have any partial or direct interaction. So far the dz square orbital will stabilizes to the lowest energy level, will become lower energy level, will gets into lower energy level, but the lower energy of dz square will be slightly higher than the lowest energy level of dyz and dzx, since the spherical lobe at the middle, right, of the dz square will have slightly negative impact of the uh, ligand sites. Right. Since the metal to ligand bond is very very shorter here, the shorter bond will have slightly closer towards the metal side and towards the spherical lobe of the dz square. Thus dz square has slightly negative impact but not have any negative interaction. Thus negative impact will makes the dz square orbital to have slightly higher energy than the dx square minus y square dz square, sorry, dx square minus, sorry, dyz and dzx orbital energy level. Right. So the energy states, if we indicate here, the doubly degenerated state, high excited doubly degenerated state, is given the Mulliken symbol of E bar, and it excited by 5.46 dq energy level, and the dz square orbital reaches to lowest energy level of minus 3.21 dq, and it indicated with A1 Mulliken symbol, singly degenerated A1 Mulliken symbol. The doubly degenerated lowest energy level indicated with E double bar has its energy minus 3.86 dq. In trigonal complex, d-orbital splitting pattern has three newly degenerated states. The E bar excited state has dxy and dx square minus y square orbitals which are interacted with ligands and excited by plus 5.46 dq energy. The A1 energy state indicate dz square orbital which is away from ligands and stabilizes by minus 3.14 dq energy, sorry, minus 3.41 dq energy. The lowest energy level gets by dyz and dzx orbitals which are totally away from ligands and stabilizes by minus 3.86 dq energy. Right. So that's how the three newly degenerated energy levels will be generated in trigonal complex. That is what E bar, A1G, E double bar. Right. The two doubly degenerated energy levels will be indicated with E bar and E double bar, and singly degenerated energy level, one of singly degenerated energy level will be indicated with A1. Right. So this is how the trigonal three coordinate trigonal complex d orbital splitting. So here I stop. Hope this will give you the perfect explanation, good knowledge about the splitting pattern in trigonal complex. So here I stop. Stay home and stay healthy. Don't go anywhere. Right. Thank you. Bye.